for making it possible for me to come and talk to you. So I welcome a few questions during the talk. So if there's something you want to ask, just interrupt me and we'll go from there. Okay, so yeah, I'll talk about the CakeML project, as you can see here. And I want to mention that it's not all my work. As you can see here, it mentions work by other people, and I'll introduce them in the talk sort of as we go along, so that you see where they contributed. Yeah, but even this list of people is not doing it justice. This list is more correct. I don't mean to you to read all of these names, but I want to show that this is a long-running project, and many of these names are actually master students who have contributed and move on. Yep. Okay, but so let's start the actual talk. What is CakeML? So first of all, CakeML, the name refers to a functional programming language in the style of standard ML and OCaml. So functional, but impure. And before you ask me what the name CakeML stands for, I just want to say that CakeML comes from Cambridge and Kent ML, because that's where we were developing when it started. But it's nowadays just a name rather than an abbreviation, because we moved around the world since then, and we've been joined by many others as well. So it's more than just a functional programming language. It's also an ecosystem of proofs and tools built around that language, including a verified compiler, which I'll talk about more. And then sometimes we also mean the verified stack that it's part of, and I'll talk about that a little bit later and also explain what I mean by verified stack. Also, to understand the setting here, CakeML was developed in an interactive theorem prover called Hall4. You might have heard about Koch or Isabelle Hall. Hall4 is a similar system. So in this talk, it consists of two parts. The first part is longer than the second one. In the first part, I'll talk about the core of the CakeML project, the research questions, main ideas, and so forth. And the second one, I'll talk about extensions and collaborations, also potential for new collaborations. So I start by research questions. These are sort of the central questions that have gone through the whole project. So we start with things like, is it possible to have a clean, high-level programming language formalized with a compiler that generates code with good performance? And can we have everything properly connected with proofs and even transport proved properties down to actual machine code or even hardware? And of course, we're not the first project to look at these questions, and one notable project that has looked at similar questions is the DeepSpec project. Okay, but let's go to the really start of the CakeML project, which was around 2012. In around that time, it had become common to use so-called code generators, and Koch users call this code extraction, to generate code from interactive theorem provers. So if we look at an example, so in the logic, you might have equations describing list append. So you have the first one saying that, you know, appending the nil list onto a list is just that list, and cons just moves the cons to the outside. And those are nice equations for logic. And so the ITP's code generator might produce standard ML code as follows from those equations. You can see that the first line of the code, generated code, very much corresponds to the first line or first equation in the logic. And this looks rather uncontroversial, right? It looks like a one-to-one mapping. So that's what these tools do. They try to be as direct as possible. But there are some non-trivial cases. So for instance, what do you do when in the logic you have head defined and it leaves the nil case unspecified? And this is not just a local thing. These kind of under specifications propagate. Suppose you then map head over x's. Suddenly this is a property. You need to worry about each element of x's. And of course, this was generated somewhere else. Then there's also semantic mismatches. If in the logic you say if x is equal to y, well, higher order logic, such as Hall uses, is very powerful, and you can have X and Y can be function types, which is perfectly fine in a logical setting, but in a programming language, you can't compare function values. And then, of course, most programming languages have finite with integers, but in theorem provers, we tend to like to talk about the mathematical integers or natural numbers. So we also have mismatches when it comes to arithmetic and so forth. Okay, so this led my collaborator and me to have a conversation roughly along these lines. Scott Owen said, this is not a good state of affairs. And I said, well, automated translation is better than manual ad hoc transcription. And he said, well, yes, but ITP should do more. ITP should prove that the generated code is behaviorally equivalent to the original functions. And this being Scott talking, when he says this, he means with respect to an operational semantics of the programming language you're targeting. And I completely agreed with this, and then we set off to do it better than the state of the art then. And the result of this was that we formalized a subset of standard ML, which later came to be called CakeML, and developed a proof-producing code generation tool for Holford. So what do I mean by that? I'm going to explain what I mean by this, but first, let's do a little detour. So first, I want to just show you a little bit of a script of Holford. So this is what I think many people who just sort of glance at interactive theorem provers think theorem provers are about. So you have definitions and some proofs. So let's have a look. We have a definition of the factorial function in this case, and it's the traditional, the most obvious definition. Then we have the tail recursive version with an accumulator, and it just uses accumulator. And here we have a theorem that relates the two. And what we have here is mostly unreadable text, that is the tactic proof saying how to prove that goal. This is, I mean, here we can see what it's doing. It's doing induction and then some rewriting and then some more rewriting. But in general, as these go bigger, you can't really tell what's going on unless you're actually running this interactively to see what the prover said. But the important thing is that there's definitions, and goal-directed tactic proofs. That's the majority of what you do in these provers. But there's actually more to them. So when the prover responds, you can see some of the generality of them. In the prover's response window, it says val fact it correct is equal to this thing which is of type theorem. And this type actually is about the whole thing. So this is because Holford's prover, the Holford prover is built on top of a standard ML read-about print loop. So you have an entire programming language at your fingertips when you're working with Holford. Many people don't use the DAF power, but I'm just saying it's there. And the whole prover is built in such a way that it has a protected type called theorem of proved statements, and you can program it with these objects called theorems. So proved theorems are just values of type theorem in standard ML, and you can program with them, but they're restricted in such a way that only the kernel of the prover can create anything of type theorem. Okay, so the fact that you're in a read-about print loop of a real programming language means that Holford is highly programmable. So now let's go back to what I said, that we made a proof-producing tool. So when we developed the tool, which we call Translate, this tool generates CakeML AST and automatically proves correspondence between the original function that was given as input and the CakeML AST that was generated. So this is what an interaction with the tool looks like. So this is a user input. We say, please translate, I mean, calling our own function, the factorial definition that we had from earlier. And then we say, oh, and bind the result to this thumb name. So then the first thing it does, it says translating factorial, and then it proves this theorem which relates factorial with a new thing it has defined. And this happens to be a value, a CakeML value that contains the AST. So there's a function value that contains an AST for the code that corresponds to factorial. And this, although it looks like a type, is actually a refinement invariant that says how these two relate. Yeah. So this is a proof-producing tool because for each run it proves a theorem as output. Right? I mean, if there's something you wonder about, then please stop me and I'll explain more or slow down. If not, okay, yeah.
I don't know much about formal methods, but if I understand correctly, I write a function in your environment, then I ask the environment, the IDE itself, to generate a theorem for that, and it proves it automatically, and everything is done by the tool.
That's right.
But how does it know what the theorem should be?
Oh, in this case, it is. It's easy in that you give it factorial, okay, and it knows then I need to generate some CakeML value that corresponds to the factorial function. And so it needs to produce a theorem that relates these two, and then it needs to find some way of some relationship to relate them with. And that is based on the type of that. I mean, this looks a bit like a type, but it's really derived from the type. So this, if you give each of these a number, then they will produce numbers that are related. That's what it says.
So what it's doing is that to generate the theorem, it looks at the type of the inputs to the function.
That's true, yes, and it also looks at the syntax of the input. So it inspects the internals of factorial.
What if the function is very complicated?
Then you have a very complicated thing coming out there. And this is, I mean, this is based on the types. So if you have very complicated type signature, then this is a long type signature, type signature-like relation. But thank you.
So a little thing, what is it saying translating FAC instead of FAC underscore there?
Because factf is the name of when you run this, we have said that this equation is called factf, while the actual function is called fac. Yeah. So yeah, and it just prints I'm currently translating that. Okay, so in terms of a diagram, this tool looks like this. You give it as input a function in logic that looks like a program, and it will synthesize an AST and produce the AST. And I have this dotted box around it because it's a proof-producing tool. Okay, so at this point in the project, Ramana Kumar appeared. He was a PhD student looking for a project to do. So, so he thought, well, you know, you don't do much with an AST unless you have some compiler or something that can make it executable. So he developed together with Scott Owens and me a verified function. So now it's a blue box because it's a verified function. This is proved once and for all. Whatever input you give it, it will produce machine code that has the same behavior as the input. I use a different box here because this one produces a proof for each run, while this is proved once and for all. Okay, so this means that if we input the factorial function here, we can run this toolchain and we get out machine code for which we have a theorem stating that the code that we get out behaves exactly like the factorial function that we put in. Okay. So we wanted to scale this up a little bit. So we asked ourselves, can we compile the verified compiler with itself? Can we do compiler bootstrapping? And here's the idea for how we did that. So we needed a normal front end to the compiler. So we have concrete syntax as the input instead of functions in logic. So this is really just a list of characters. That's what it is. It goes into a parser, it goes through type inference, and then it goes through a compiler backend. and out you get machine code. So I put all of this in a yellow blob because all of this is one giant functional program in the logic. I meant to mention Michael Norrish here because he provided this parser and has generally been, from this point onwards, very influential in the project. Okay, so the point is that the yellow cloud here is a function in the logic, and that's exactly what this takes in. So what we do is feed the CakeML compile function into this front end to our toolchain, and out comes the generated code that behaves like the CakeML compiler function. Some people think this is just magic, but I'm getting better at describing it. Any questions on this? Okay, no, everything's clear. Good. So this was version 1, quite long ago actually now. So everything was bootstrapped and everything would fit together, and we were happy about that. But we were not so happy about the details. So we were not happy that the compiler had very few optimizations and was very basic in many ways. So since then, the project took an emphasis on how can we sort of become more realistic. And then the question of how real can we make CakeML? And particularly, we wanted a better execution speed of the generated code. We wanted better support for I/O, and we also generally wanted a better methodology for doing all of this. So we, after some exploration, we settled on a new methodology, which we call functional big step semantics. So I'll give you a very brief introduction to it. Operational semantics are usually written as rules, an inductively defined relation, but we define it instead as a recursive function, and just like you'd write an interpreter for the language. So here we have eval of a constant just returns the number. This is not CakeML semantics, but this is just an example of a semantics written in this type. A variable just looks something up in an environment and then returns it or fails, and so forth. A let first evaluates the thing the expression we want to bind the value of. We get the value, and then we use, this is monadic syntax. There's a state and exception monad. Once we have a value, we bind the variable name in the environment and then continue evaluation of y. So there's a big step because we're really evaluating both x and y and then return. So it's not a small step. You might then wonder, wait, how do you make sure this evaluate terminates? Because we're in a logic and they're all functions that are, they need to be terminating. Well, we can kind of see the trick, or I can at least describe it in terms of the call. So suppose we have a call instruction or expression, then we evaluate the arguments to the call, we get some values, and then we fetch the body to run, and we evaluate the body. But there's a hidden trick here. This get end and body function also decrements a clock, a so-called fuel parameter, that's hidden inside the state, which means that we can only go through so many calls, and then it'll terminate. We say that a whole program terminates if there exists some amount of fuel that will get it to successful termination. And we say it diverges if for all values of fuel, it always times out. Okay, so that's the idea of functional big step, and it worked really well in our proofs because everything's an equation, and that works well because we can use rewriting when proving things. Okay, so in our search for realism, we then developed a new compiler, and this has 8 intermediate languages and many optimizations within those. And each intermediate language was designed to be at the right level of abstraction, both for the benefit of proofs and compiler implementation. If you look at non-verified compilers, they have many fewer intermediate languages. And this, I think they can get away with it, but when you're doing proofs, you want to have it at exactly the abstraction level that's convenient for proof. So that's why we have more intermediate languages. You see the same phenomenon in the CompCert compiler. So I'll zoom in, and I'll also, I should mention, at this point in the project, Yongkian Tan, then a bachelor student, later on PhD student at CMU, and then graduated, but still active in the project, joined the project, and he was really crucial to making this new compiler happen. Okay, I'll zoom in, and then I'll sort of go through this unless you stop me with questions. So this column explains the values. Here are the names of or descriptions of the languages involved, and here's a comment on the transformation being done. Parser and type inferencer at the start of compilation is same as version 1. Yes, they're both proved. Early phases of the compiler reduce the number of language features, and then this clause adds a language feature, which we use for optimization. So it adds multi-argument closures. Closures are function values. This is very important for good execution of functional languages, is to have multi-argument closures. Then, as compilation progresses, we eventually arrive at a first-order functional language, which is very simple, actually. And then eventually we then arrive at an imperative language, which is still a lot of data abstraction. And then we do a big step here, remove data abstraction, with which we arrive at sort of C-like abstraction level. So we suddenly have a machine, integers, and we have pointers. And the rest of the compiler is roughly a C compiler with a functional programming twist. In particular, we have a garbage collection primitive in this language, and we have it optionally there, and here we implement the garbage collector there. It's a verified garbage collector that gets made part of the compiled program. At the very bottom, we compiled 5 different target architectures, and we have both 64-bit and 32-bit architectures, and big endian, small endian. All of this variety at the bottom meant that we had to keep everything quite parametric higher up.
Can I ask you something about the very top one?
Yeah.
So what does a correctness proof for the parser look like? What exactly will you prove correct?
So we proved, so we have a declarative definition of what the grammar is. And then we have the peg parser that actually implements that. So then the soundness and completeness is that if there exists a parse tree, or every parse tree it finds, it will be according to the grammar. Okay. And if there is a parse tree, it will find it. Yeah. That's what we prove. Similarly for types, if there is a way to type the program, we will find it. Yeah. Now I'll just skip ahead. Now I want to show a bit of performance numbers. Here, these are all different kinds of ML implementations. So same language family. And CakeML is the light blue one. And everything standardized according to the speed of native code compiled or camel. So higher means slower, it's worse, and lower means better. And we can see that Milton is generally the best one, the dark blue one. But my point here is really that if I remove these names, I think it might not be so obvious which one is CakeML. I mean, yeah, maybe these are giveaways, but the point is that CakeML's speed is in the same ballpark as the others. And so we're quite happy with that, because these are serious compilers. These are competition, so to say. So these are micro benchmarks. Oh, I have some bubbles here. We have some reasons to believe why we're slower, but I won't go into them. Here's not a micro benchmark. This is a much bigger program. So here, the green one is the CakeML verified checker for UNSAT proofs. So LRAT proofs. And here we have an ACL2 verified binary, and here we have a COC verified. And the higher you are here on this graph, the better. So this is a percentage of proofs checked of the SAT competition. And here's the time limit given. So the longer you give it, the more we check. So we're, even though we're more verified in some sense than the other two, we're still tracking the sort of the better one of them very closely. That's the performance. We're quite happy with the performance. And now I thought I'd show a demo just very quickly of this running. So this is a CakeML that checker running. If you forget to give it arguments, it does that. But now we give it a CNF file to check and a proof of that UNSAT, and it will wait a little bit, and then it has proved UNSAT in well, 4 seconds in this case. And now I'm going to show quickly the program that actually ran there. So I'll just zoom ahead in this now. Yeah, so the program that actually ran is this. So this is what was generated from the theorem prover. In the theorem prover, we arrive at these are the bytes, the machine code bytes of the program, and that's what we actually run. Okay, and then we also have different ways of manually verifying CakeML code, because previously I showed that synthesis tool that given a function, you can have it generate CakeML code for you. The problem with that is it generates pure code only. But to get performance numbers like the previous, we have to use imperative features like arrays and so forth. So we use this Arthur Chargarod's CFML framework, which RML adapted for CakeML code, and then somehow improved. So we have this separation logic, horse-style reasoning about impure CakeML code that we use for verifying those parts. And then I want to talk a little bit about infinite runs and liveness. So the compiler proofs, we proved that the compiler, or a lot of the compiler proofs are about divergence preservation as much as termination preservation. So if the source program you give diverges, then so the correctness proof, any correctness proof for that should also carry over to the binary. But this has a funny mismatch, because the program logic and most program logics don't talk about infinite runs. They just say, in the standard Hoare logic way of saying, either if it's total correctness, it will, from this precondition, we will reach a postcondition where this holds, or in the partial correctness, if we terminate, then this holds. But we wanted something that can talk about infinite runs and the correctness of them. So we adapted the CakeML program logic for reasoning about infinite runs and liveness properties about them. So we have a total correctness program logic for infinite runs. And what we prove is then that it will run indefinitely, and during that infinite run, it will produce this stream of events. And for this, Johannes Pohjola, a postdoc of mine at the time, was crucial for this part of the work.
So do you formalize that liveness properties still in higher order logic, or you?
Yes.
But is it kind of like a style similar to temporal logic, or?
No, it's much more like a normal Hoare logic. I can show you later. I have so this is CakeML specific, and we realized afterwards that CakeML sort of obscured it a bit. People don't see the ideas of the logic separately from CakeML. So I have a different one, which is just a toy language, but where the ideas of the sort of infinite runs come through. So I'm happy to share that, but maybe after the talk. There's still a problem with liveness, that the compiler correctness theorem that we prove allows any CakeML program to exit early with an out-of-memory error. And you might wonder, why did we do that? Well, because in the CakeML source semantics, a list can be as long as you want. There's no limit on the length of a list in the abstract world. But when we compile something to an x86 processor, which say 64-bit addresses at most, well, in reality, of course, they're not that big. But anyway, you have a limit. You're going to hit a limit. So at some point, we have to allow this sort of out-of-memory errors. This comes out in the correctness theorem like this. So a compiled program, the semantics of it is in the subset of, well, the source semantic behaviors, but extended with, I think, yeah, extended with out-of-memory errors. And according to this statement, we could always compile every program to immediately just say out-of-memory error. And that would be a correct program, compilation, according to this. And we have, well, the next slide addresses that, but also experimentally, we can run our compiler and it didn't give out of memory, so it's clearly not that trivial. Okay, so the proving absence of out of memory, we did that using, we verified a space cost semantics for CakeML that allows liveness properties proved at the source language to be transferred down to the generated machine code. So with this space cost semantics, which is really making the decision here, we get that the semantics, so the observational events, externally observable events of the compiled code are exactly equal to the observational events of the source semantics. This is so we remove the subset and it's not none of this extend with resource limit. Now they're going to have exactly the same behavior. So if you prove that this diverges, then so will this. And this one has internally, it refers to the cost semantics. You have to prove that this program, when run on that input, stays within the limits given by this configuration C. So this is great. We have a cost semantics and we can prove this. In theory, doing any kind of reasoning over this cost semantics is really horrible. So that's a remaining research challenge. Yeah, so if cost semantics says the program is safe, then the semantics is preserved exactly. So happy ending to that. Oh yeah, I could mention also that the cost semantics is taking into account garbage collection. So as long as the reachable data currently is less than the heap limit, also taking into account aliasing, which happens a lot in a functional programming language, then we get, that's how it measures the space with those in mind. Okay, now I come to the second part of my talk, which should be a bit shorter than the first one. So I'll talk first about hardware. So I mentioned very early on that CakeML sometimes refers to a verified stack. So a verified stack is a computer system that is demonstrably correct. Specifically, it is a system with a formal proof of correctness that covers all layers of the implementation, from hardware all the way down, all the way up to application code. So there haven't been many such, as far as I know. As the CLI stack in the early 90s was one, very soft in the early 2000s, and now recently CakeML and Silver, my PhD student's work, and then from Adam Schlipala's group at MIT, there's also verified stack after ours. So, so where do we start with this? Well, the compiler work that I explained earlier stopped at the software-hardware interface, so at the instruction set architectures, so the machine languages here, and now we want to go below that into the hardware. So this is how we did it. We added another target. These are commercial machine languages, but this is our own invention, just to make life easy. And then here we added my PhD student, Andreas Löw, he designed a simple CPU and did a manual proof of correctness of this. So this CPU implements that machine code, machine language, and then there's an automatic proof of turning this functional specification of a CPU down to actual Verilog. And then we also proved higher up a verified implementation of an in-memory file system, so that we can run CakeML this file system on this CPU in such a way that all of the software in the system is verified. It's we have proved all of it. So in some sense, this is all, of course, a bit silly in that we are now completely in our own world, not connected to anything. But this proof did give us some reassurance, because it showed that the assumptions we make about the file system can actually be realized by some verified code. So we got a bit of assurance from that. Okay, I want to go even deeper. So Andreas Löw, who I've mentioned now a few times.
Question there. So when you say manual proof, you don't mean, so is this like similar to what you said before, the difference between the proof written once for all and a generated proof, or here you really mean like manual as in written in paper and not automated?
Well, it's manually written into the interactive theorem proof.
Right.
So it's an interactive proof.
Right, I got it. Yeah. So it's not like okay. So it's automated, except that you wrote by hand that and not generated. Right?
Exactly, it's not generated in any way. You wrote, Andreas wrote it by hand, yeah, into the prover, and it accepted it. So separately, he went on to do more. So he also had a verified compiler for Verilog down to technology map netlists, and then we wondered, where do you go down from here? The physics starts getting in the way here, and it's not so clear what the semantics is once you go further down. But we're quite happy with this. So how real is it? Well, it runs, he could run it on this fairly cheap FPGA. I mean, he could load his CPU there, and on that CPU, he could run the entire CakeML compiler. So that's a non-trivial program. Now I want to go on to the next thing, Haskell-like. So I mentioned earlier Hall 4, Isabelle Hall, and Koch. Well, Haskell-like is a theorem prover, similar theorem prover for higher order logic, and I mean, it's maybe not so famous, but it's still a major theorem prover in the sense that the Kepler conjecture has been proved in it, and a lot of other math formalizations, such as multivariate real analysis, have been formalized there, and so it's a major prover in that sense. A lot of big results exist in it. So what we wanted to do was build a verified clone of Haskell-like, which we call Candle. It's the light on the cake, so it's a candle. So this is, we have proved Candle to be sound. I'll get to that later, what it means. And one user of it said that it really looks and feels like Haskell-like. And I suspect that if we took a beginner user of Haskell-like, we could even fool them that this is Haskell-like. We tried to make it look so similar to Haskell-like. And yeah, I suspect we won't have time for a demo, but I can show you afterwards if you're interested. So Haskell-like has an LCF style design, and so does Candle. An LCF style design, as I alluded to earlier, has a logical kernel that keeps track of this theorem type, this protected theorem type. It's the only part of the system that can create this theorem type. But you write a lot of code on top of this, which then has tactics like rewriting tactics and so forth. Whenever they want to create a theorem, they have to go through the logical kernel to instruct it how to get to what it wants. So we set off to prove this soundness of the dotted region here. So the logical kernel, all the derived code, user-provided derived code, And sitting on top of the CakeML compiler, what we didn't take into account was the operating system hardware and all the sort of everything below that. So we proved an end-to-end soundness theorem for everything in the dotted area. And so what does this soundness theorem say? It says roughly that when the machine code running the prover will only output theorems that are true according to the semantics of higher logic. So this is a very far-reaching end-to-end correctness theorem, because it, on one hand, talks about machine code. On the other hand, it talks about what is true in the semantics of higher logic. So really far, very far away from each other. And this is in the presence of users just inserting whatever code they want. So this is, users are sort of malicious in this system. Can be. They can try to get unsoundness somehow, but we have proved this whole structure allows us to avoid that. So that was published in this paper, but what I really want to show, the really hard part of this, I would say, is adding dynamic computation to CakeML. So we added the compiler itself into the runtime. Previously, CakeML's runtime had a garbage collector and a big num library, but now it has the entire compiler itself. So it can compile new code at runtime and install it into the running executable. That was a major effort that I want to just point out that Thomas Sewell, he wasn't in that effort from the beginning, but he's certainly the one who managed to get it over the finishing line. He was key to that. So thanks to him for that major effort. Okay, that's all I want to say about Haskell-like. And then now I'm going to talk more about future directions of this work. So one of the aims we have with CakeML now is to use it to build compilers for other languages than CakeML. And for that, we have a new Haskell-like compiler for a Haskell-like language. And just, I won't go into the details of it, other than just give you the sample code of what it can compile. It can compile programs like this. It looks like Haskell, right? It has an IO monad, and it has Haskell syntax, and it has Haskell lazy evaluation. And like the CakeML compiler, it also has this big diagram. But note, in this diagram, we start from pure Cake source code, and we end at CakeML source code. So now this is just using the entire CakeML compiler as a backend. So that's what we hope to do in the future, to use the CakeML compiler as different kind of backend for different projects. And finally, I want to talk about proof checkers and collaboration around that. So some tools generate proof traces, files or logs of some kind. For instance, SAT solvers produce LRAT proofs of UNSAT. Whenever they say something is UNSAT, they output this kind of proof. And then you can have a verified checker go and check that that proof is actually well formed. So we've found that verified checkers, the whole area, is a good application area for CakeML tools. So this is also a good opportunity for collaborations, because, we have, for instance, collaborated with Myreen on this checker for LRAT or LPR proofs for UNSAT. And that was very, we learned a lot about SAT proofs in this process. And of course, the checker is a byproduct of this learning and implementing for it. And it also, I have a demo if you want to see it afterwards. I mean, you saw that demo already. And then we took after we've done this, Jakob Nordström's group contacted us, and they have a similar but more general tool called VeriPV for pseudo-Boolean proofs. So these are instead of CNF formulas like SAT checkers, SAT solvers deal with, these generalize those clauses to have a linear arithmetic. And then most recently, we also have we're working on a similar verifier for integer programming results. And this really stretched the CakeML's compiler's bignum library to the limit, and we realized it needs to be improved a bit. And we also have a verified checker for floating point error bounds. So that brings my talk to the end. So the CakeML project has developed formal semantics for standard ML style language, a Bootstrap verified compiler, scalable proof-producing code generation, a separation logic that can talk about non-terminating code and liveness of that, a space cost semantics, and some verified applications. And yeah, current work is implementing other compilers for other languages. And if you have some verified, some sort of proof log that you want a checker for, then let us know. And I mean, we should collaborate on that. And that's all.